Greetings everyone! Today we're going to explore graphing absolute values, but today we're going to use transformations. Now this is a big topic because we're going to use transformations for every function that we do this year. So this process is going to be newer. We're going to have to keep working on it, and make sure if you're struggling with any part of this, you let me know right away so we can work on it some more. We do have a foldable for this. You can access it on Google Classroom or in the class. And of course, if you don't have it, just write it down in your notes. Now, this is not on your foldable, but I need to address the idea of a parent table. We've talked about a parent function, right? So let me jot this down. You don't have to write this part down, but if I give you this function, let's say, and we worked on this before, the parent function of that is take away all the moves, right? What's the bare bones of this function? The bare bones is this is an absolute value of x function, right? So let's think of a bare bones table. The parent table for the absolute value of x is created. We have to create it each time. If you're a good memorizer, great, you're going to be able to memorize this, but we're going to figure it out each time. Meaning, let's go back to Algebra 1. We're going to use those same typical 5 values, right? Remember how we always did that in Algebra 1? And what we're going to do is we're going to plug those x values in for x. So the absolute value of -2 is 2. Right? I'm just finding the y value. I'm plugging it in. The absolute value of -1 is 1, 0, 0, 1, 1, 2 is 2. Okay? So if you're a good memorizer, you're just going to memorize that table. If you're not, all you have to remember is plug in the same 5 values every time and calculate the y values using the parent function. So I'm going to reuse this table on every little piece of notes, okay? The first tab we're going to look at is a vertical shift up. Keyword vertical. Vertical implying y-axis. When we open that tab, we're given the function f of x equals the absolute value of x plus 3. And so the rule that we're going to keep working on is when you add a value to the outside of a function. Notice how it's outside the function. That means that we're going to shift the graph up k units. It's a vertical shift. So up because it's positive, and k just represents the number, how far. Okay, so I see a plus, and we're going to go up 3. Now, if this is my parent function and that's my only shift, and if all I ask you for is the graph, you're going to shift every point on that graph up 3. That's it. Okay? But where we need to extend our thinking and what we're going to work on is our parent table. So go back to the previous slide if you need to, but remember that parent table that we calculated for the absolute value function. And if this is a vertical shift, if the plus is on the outside, vertical means we're going to add 3 to every y, or every vertical value. And what that does is it creates a table that shows every point that we just graphed. See how that works out, how that matches my new graph? Now you might be thinking, Mortvet, I thought we were getting away from tables. Parent table work is different. It's not going to seem efficient yet, but it will. Vertical shift down. Let's look at that tab. Well, just think it's the opposite, right? So if I have a function of the absolute value of x minus 3, or if I have something being subtracted from the outside, like a 3, that means it's shifting the graph down k units. Down because it's negative, k is the number. So this particular graph here, okay, if I take every point and I move it down 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. right? I'm going down 1, 2, 3. Then I could see that graph shifted. Let's prove it using the parent table. So if this was my parent table originally, remember, original 5 values, plug them into the absolute, vertical shift down 3. Vertical means y-axis, down means negative. If I calculate those y values, then I have my new graph. Whoops, oh my goodness, can Mortvet count? There, wow, whoa, -2. Okay, sorry about that. Remind me, if you watch this, to mark this on my mistakes board, okay? Alrighty, that table just proved our green graph, our shifted down graph. So vertical shift is the y-axis, and it's on the outside of the function. Let's jump to horizontal shift. Well, horizontal implies x-axis, x values. So if I have this function, you'll notice the -3 is inside. If I have a subtract h on the inside, look where it is, it's inside the function, then that means we shift the graph right h units. Oof, this is tough. Look at how this works. The negative implies right. That's the opposite of what our brain wants to think, right? So if it's inside, it's always the opposite of what you think. All right, so let's just try a quick graph. If this is my parent function, and mine says subtract 3, that means shift every point right 3, right 3, right 3, 1, 2, right 3, right 3. I moved or slid, or hey, let's talk about geometry, translated my function right 3. Now let's talk about the parent table. So we're going to keep using this. We'll tie it all together in the end. That parent function, it says horizontal shift. That means I'm going to add 3 to every x value, horizontal, which creates the graph that we drew in green. See how that matches up? Therefore, the opposite has to be true. If it says horizontal shift left, then it's exactly what you think. Inside the function, or with the x, see how they're next to each other? X, the numbers with the x. If it says plus h means left h units. A plus means left however many. So if I have my parent function that looks like this, and I'm saying plus 3, that means left 3, left 3, left 3, left 3, left 3. Now, table-wise, parent function creates our parent table, and look, it literally says x gets a 3. But we have to remember it's the opposite. That's going to be the toughest part out of all this. The x shifts are always the opposite of what you think they'll be. Okay, but we've created our nice new table that matches what we already graphed. Now let's try something that some of you noticed when we did the table worksheet. Vertical compression. Okay, if I have, and here's how I remember this idea of compression. If I have a V and I compress it, meaning I've got this machine that's going to put downwards pressure on the V. It's going to compress it, right? That's what I think of when I think compression. If I push down on that V and then I push down on it more, right? If I've got this machine that's pushing down, it's going to widen the V. It's going to widen it. Now, you don't have to have that memorized. It's a good visual because our table work is going to help. So if I have a factor out front of A times the function, any function. If A is between 0 and 1, it is a compression. And we're going to multiply the y values by that factor. And you might be thinking, well, how do I remember its y values? It's called a vertical compression. Or if I'm compressing with that machine's coming down. Down means y-axis. I'm pushing the y values down. So that might help you remember that we're going to multiply y values by A. Now, here's our parent function. I'm going to actually show you the table work first. So, parent table, right? We've got our same 5 x values. We know if we plug them into the parent function, we've got this. Today it says 1/2 on this example. We're going to multiply the y values by 1/2. Vertical compression, multiply, condense by 1/2. Okay, you can think of it kind of a lot of different ways. So we've got a 1, a 1/2, a 0, a 1/2, and a 1. Watch what happens when I graph that. -2, 1, -1/2, 0, 0, 1/2, 2, 1. See how it became wider? I cut every y value in half. It was compressed. Okay. Now let's try the opposite. What if A is not between 0 and 1? If it's not between 0 and 1, we have a stretch. So if I have an A value that is being multiplied by my function and it's greater than 1, then that means I'm going to multiply the y values by A still. And we call this a stretch. If I elongate or stretch my V, it's going to make it skinnier, right? Imagine grabbing the V and pulling it up. We're going to stretch it. So I'm going to approach this from a table perspective first. Parent table. We're going to multiply. It's a vertical stretch. Oops, why did I put negatives? Parent table's positives. Sorry about that. Stretch means multiply the y values by the factor out front. We're going to create our table. So now you can see that that's going to make my y values larger, which means it's going to be skinnier. If I graph those points, I'm going to have -2, 4, -1, 2. See how that's skinnier already? If the A factor is greater than 1, it makes your graph skinnier. It stretches it. Now, what if its A value is less than 0? Right? Well, then that's just a negative, and that's its own rule. Anytime I have a negative in front of my function, that's a reflection in the x-axis. That's my flip down. This is going to be one of the easier ones to remember. And if we're going to apply it to the parent table idea, technically it's like we have a factor of -1 being multiplied, right? So parent table-wise, that means I'm going to multiply my parent table by -1. So it's not changing, it's not compressing or stretching. All it's doing is flipping those values down, right? And we could have graphed that without this table. I think that knowing, even if I don't finish my table, I think you know that a reflection down is going to look like that, right? But my parent table confirms it. Now you have a small example here in your notes. It looks like this. If I ask you to describe the transformations, I would say there's 1, 2, 3 pieces, right? So we would need 3 pieces of information. So first of all, the 2 is a vertical stretch of 2. Okay, you are going to be asked this in the future. The -1 inside is a horizontal shift, and be careful, right 1. And then the -2 is a vertical shift, down 2. Okay, that's what we got to work on, is first describing the pieces. Now, parent table wise, we're going to multiply the y values by 2. That's my vertical stretch. We're going to add 1 to my x values, and we're going to subtract 2 from my y values. Now, let's approach it from a parent table perspective, okay? -2, -1, 0, 1, 2. My parent function says just take the absolute value of all that. Now, here's what's cool. You just read your function left to right, meaning the first number I see is a 2, and it's being multiplied. So we're going to multiply the y values by 2 because it's a vertical stretch. Vertical meaning y. Don't solve yet. Here's where this table becomes so helpful. Horizontal shift, right 1. Horizontal, x-axis. If we're going right 1, we're going to add 1. Vertical shift, down 2. Vertical meaning y. We're going down, so we're going to -2 from every value. You can do every move and then create your final table. So watch what happens here. We just created our final table without having to plug in a lot of table work. I see the symmetry. I can graph my dots. -1, 2, 0, 0, 1, -2, 2, 0, 3, 2. And this makes sense. It's stretched and it's skinnier. Perfect. It went to the right 1 unit from the origin. Yep, sure did. And it went down 2. Yep, my vertex is down 2. Okay. So that parent table work, instead of plugging in random x values into the whole function and calculating everything, we didn't need to. We just added and subtracted some numbers. Now, I'm going to try one big problem altogether. I know this is a long video. If you understand and you can move along, great, but let's do one more example. First of all, I'm going to describe all the transformations. This would look like a learning check problem, right? So the first thing I notice is the negative, okay? Negative means, my first description, is reflection in the x-axis. Next, I see that I have a 2 out front. So that is greater than 1. So that is a vertical stretch of 2. Next, I see a -3 with the x. If it's with the x, it's a horizontal shift or slide right 3. Remember, it's opposite. And last, I have a +1 on the outside. That is a vertical shift up 1. We have 4 moves going on. I'm going to take care of some parent table first, okay? So, parent table is -2, -1, 0, 1, 2, 2, 1, 0, 1, 2. Now, the red and the yellow, that whole factor out front can be taken care of in one move. They're both going to deal with the y's. So I'm going to multiply all the y's by -2. Vertical stretch, it's on the outside, so it applies to the y's. Inside, I've got x's, and so I'm going to add 3, since it's always the opposite value inside. And lastly, we're going to add 1. Now, the order does matter. If you add and then multiply, that's different, right? So just read the function left to right. So my final calculations would be 1, 2, 3, 4, 5, negative 3, negative 1, 1, negative 1, negative 3. I'm just calculating those, right? So I'm going to graph 1, negative 3, 2, negative 1, 3, 1, 4, negative 1, 5, negative 3. Now I'm going to just extend. I can see the change over time. I'm going to extend that because I figure I might need that intercept, right? All right, the vertex, the center point, is always going to be in the middle. So that's 3, 1. It's neither because it's not reflected in the y-axis. It's bounded above, meaning there's a wall above that's blocking my graph. Increasing, decreasing. I am increasing from negative infinity to the x value of 3, and I'm decreasing from 3 to the x value of infinity. If you need help with these descriptions, see the Describing Graphs video. I have no minimums. My maximum is absolute and local at the vertex of 3, 1. The domain of an absolute value is always forever left, forever right. My range is from negative infinity up to the y value of 1. Yes, you need a bracket here. My graph is continuous, and I do have several intercepts, right? I have the y-intercept of, let's see, 1, 2, 3, 4, 5. So 0, negative 5. And I do have 2 x-intercepts. You might be thinking, how do I know what those are? They look like halves. And because you know you're kind of going down to right one, you can assume those halves. So we could say 2.5, 0, and we can say 3.5, 0. Now, if you want to talk more of the algebraic reasoning of why, let me know. We can certainly work on this. So this is an overall big picture, every transformation possible example. I don't have a note sheet for this, so maybe consider screenshotting this, saving it, or revisiting this video when we get to that point of whole picture. I know this was a long one because it's a big concept, it's big ideas, and we're going to use this idea on every function in the future. So as always, though, make sure you check Google Classroom. What is the task for today? Let me know what questions you have, or take a look at the Sabre Center schedule. And until next time, have a good one.